Thank you, Razvan. And now let's give a round of applause to Jonathan Hulme. First of all, for being a gold sponsor for the event. And you have really good coffee outside, sponsored by you.
That's
very good.
Right, yeah, thanks everyone for having us. It's good to be here after so long of not being able to see all of you guys, so it's really good, different venue, nice and exciting. So I'm just wondering, out of everyone here, can you tell me, did anybody remember or see my talk that was like 2 years ago? Oh, great. That's wonderful. Yeah. Okay, so the reason I'm asking is because what I'm talking about today is what we kind of failed to do before. So we had a problem, we tried to fix the problem before, didn't really work out, and now I've got a nice story for you about what we've done since then and how it's progressed. So lots of different ways of doing these types of problems that you may come across, and yeah, we've just basically found a different way to try and accomplish what we've done. Probably wouldn't have been the way that we wanted to, but yeah. So first off, a bit about myself. So yep, I've done the whole computer science thing. I'm a programmer day by day, so I still do lots of programming. Sort of do full stack, but I'm more working towards the top end of the interfaces and stuff. I've been a VoIP engineer for 10 years. So yeah, lots of time working with OpenSIPS, working with Asterisk and FreeSwitch, and all of these other things. And yeah, OpenSIPS is a really cool tool. There's lots of things you can do with it. Unfortunately, some limitations as well, and that's kind of why I'm doing the second talk rather than just the first one. Yeah, so I've also got the entrepreneurial side. I've been developing a couple of VoIP companies. We developed some VoIP companies in different countries. But these days, I'm less into building companies, more focused on this single one, building this tech and solving some really interesting problems. So the company that I'm at now is Connex, yes. So this one I founded in 2014. We've built essentially a cloud soft switch. And the target audience for this is other carriers, small carriers, people who don't necessarily want to manage their own infrastructure, but they want to be a carrier nevertheless. We've got a global customer base, so we have customers most continents. You can probably guess the ones that we don't, but all around the world, connecting from different networks, different latencies, different speeds, calls routing everywhere. So it's interesting. We've got over 250 OpenSIPS deployments right now on our cloud. All of these kept up to date and managed. We've got some nice continuous integration stuff in certain places going on and automated deployments. So it's kind of easy to manage, but it just does mean that you get much more opportunity to see lots of different problems that are coming in. Oh yeah, and I'm really pleased that I was able to help to contribute to the audit, and I think that any time that we get things like that to sort of improve the open source code quality base, it's really, really important. I haven't actually programmed anything for OpenSIPS myself, but I'm always there trying to say, yeah, we've got this problem, we need it fixed. We got this one, and you know, let's get them all fixed. So, if you did remember the talk before, I'm going to go over some of the same things, but we launched this in 2014. There's various things that have been happening in the middle. We added load balancing. We've done some native clustering in OpenSIPS, so that's kind of cool. As soon as we learned about how to do that feature, yeah, we wanted to give that one a go. And then we built the Anycast network. As soon as we learned about Anycast, and the fact that OpenSIPS deployed it, we went ahead and deployed it. And as far as I'm aware, I think we've got a pretty big Anycast network in terms of the traffic that flows through it, which again has brought its own challenges. Again, I've been pushing back on the OpenSIPS team to try and get some of these bugs fixed so we can achieve the throughput that we need. So that was fun. 2020, this is when I sort of gave this other talk. And the problem that we've got, again, I'll tell you a little bit more about it in a bit, but we wanted to do globally scalable RTP. I'll give you the use cases in a sec, but we didn't do it, and it just wasn't it wasn't a high priority. So we moved on, we played about with programmable voice, got some nice APIs and more as a class 5 application level services. We did a few of those, and now we're back to the same problem again. It's came back around. So why do we have this problem? This is to do with, the title of the talk is Circumventing RTP Engagement Blocking on a Global Cluster. So there's a little bit of a mouthful there. So I'm going to show you by an example. So everybody talks about Alice, Bob, and Charlie, but that guy's Delta. He's the next one. And he notices that Alice and Bob are making lots of calls. So he sets up a telco just for them. He comes to us and says, yep, I want to set up a service to be able to connect calls from Alice to Bob. So we start off, Alice is in New York, Bob is in London, and Delta deploys our service to facilitate calls between them. So let's have a little look how that goes. So typical way that this is engaged, we've got Alice sends an invite packet over to the SIP server. SIP server talks to the RTP server. Then the invite packet continues and goes over to Bob. Bob will then send a reply. It'll go down the RTP and go back. And then Bob will be engaging that RTP. Alice will be engaging that. It's pretty simple to what you've just heard. For this scenario, not a problem at all. We have got latency in between, but the setup's pretty quick because OpenSIPS is located right next to the RTP, so we don't really have any problems. But now we've got a little bit of a different scenario where the SIP server that we've just deployed for Delta is over in New York, and Bob is in the UK, and now Bob wants to call Charlie. So you can see the entire media has now been passed all the way over to New York, but Bob and Charlie are both in the UK, so simple problem to solve that, right? We move the RTP server to the UK. We don't have to deploy another SIP server. The latency on SIP is not really a big deal. But now we've introduced a new problem, and that is that the SIP server that's in New York has to talk to the RTP server that's now in London. So we've got this latency in between. Now, obviously, there's probably other ways that you can solve this. You could deploy a server in London as well, but as soon as you start getting lots more people talking in lots more zones from different places, you don't necessarily want to have to deploy a server in every single place that they're talking from. So to have RTP decoupled from SIP can be really useful at times. So that's the way that we've essentially got it. We've got our SIP servers on a completely separate platform than our media. It means that we can control them separately, we can deploy different types of hardware, focus on different metrics for what we see coming in and out. We've got flexible routing. We can do the whole dynamically move calls. We can spin up more servers as they need to with elastic capacity. So it's a really powerful thing having these two separate. We do reduce the single point of failure, and we can avoid congestion. So when we deploy this, we've deployed this quite a few times over, we start to notice a couple of problems. The problems are as SIP starts to just behave slower. Packets start getting delayed and packets start getting lost. And this is essentially what we find in the logs. So yeah, some people have seen this before. This is sort of what happens when it gets overloaded, and this is because of a blocking event. We didn't really know exactly why this was happening when we first saw it. So we did this exec message threshold. This is something that we can set at the top of the OpenSIPS config. This is really useful because what it basically does is it logs out any functions internally to OpenSIPS that are taking longer than a predefined amount of time. So when we did that, we got something like this. I'm not really sure if you can see that, but amongst the ones that are taking up all of this time, we've got our RTP delete, RTP answer, RTP offer. So the problem's absolutely 100% to do with media engagement. So why does this matter? Well, if you're dealing with one or two calls, it doesn't particularly matter because if you've got 30 processes, assuming that we've got an offer answer latency time of 150 milliseconds, which, yeah, I know London to New York's more like 90, but let's say it's 150 milliseconds. Each call is going to be locked for an offer, for an answer, for an update, not to mention any re-invites. So the maximum amount of throughput that you can get for engaging a latent zone in this scenario is around about 60 calls per second. that's okay in a lot of respects because not everybody is sending huge volumes, but we had the scenario where we did. Now, what we wanted to do a couple of years ago was we wanted to attack this whole asynchronicity problem within OpenSIPS. So we've got here where we perform an RTP engagement, RTP engine offer, and it's blocked, and you can't do anything for those 150 milliseconds. What we essentially wanted to do was something that looks a little bit more like this. So we essentially put an asynchronous callback on the RTP engagement, so when the message, when it sends it off, it can go ahead and do something else. That process is not locked. So this is this whole asynchronicity thing, and there's a whole difference between asynchronicity, parallelism, what we can have serial, what's blocking, and everything else. So just again, a very quick question. How many people are completely comfortable with the concept that about synchronicity, asynchronicity, and also, more importantly, parallelism? Just everyone good with that? That's fantastic, because I'm going to tell you about that now. So I love my robot Hoover. My robot vacuum cleaner can go away and do things, and this is an example. So if I start one vacuum cleaner, I push the button, and I watch that, and I just look at it all the time, that is a synchronous operation. I can't do anything else. I'm stuck looking at that vacuum cleaner. I'm bored. But it's not parallel. There's only one of them, so no parallelism, no asynchronicity. We're talking about synchronous. That's what we got now. Now, let's say I run another robot vacuum cleaner, and I push the button, but I go away. I walk off. It's asynchronous now. I'm not checking on it. It's going to go ahead. It's going to do its thing. And when that's finished, it might interrupt me. It might give me a little beep, or I might go back and check on it. That's what we got. Asynchronous, nice and simple. It's not parallel still. There's only one of them. So now I've got three robot vacuum cleaners. I start them, I walk away. They're asynchronous, same as before. I can do other things. And I've started all three at the same time. They're parallel. So we've got asynchronicity and parallelism going on. Again, they're going to tell me when they're done. So now we've got the last one is I start three robot vacuum cleaners to schedule them at different times. Now, if I schedule them and walk away, let's see here. They're asynchronous. I can do other things, but they might not be running at the exact same time. So if they're not running at the same time, they're not parallel. So that's a little bit of a brief on the differences between asynchronicity and parallelism. Now, the reason that that's important is because OpenSIPS does parallelism. You can spawn up multiple processes. So you can, here we've got 10 process workers, and messages are synchronous. But OpenSIPS 2.1 saw the capability of processing messages asynchronously. These are the asynchronous functions. Notice no RTP engine stuff. And this is what we wanted to have asynchronous. So we really wanted it to do that. We had success doing it in the request route. We had success doing it in the reply route. We couldn't do it in the branch route. It's a bit complicated, more than I'm going to go into now, but it's right to do with the lower levels on how OpenSIPS works. So, and also process parallelism can't make up for asynchronous operations. You can't spawn up hundreds of processes efficiently. It's better to check back later. So this is OpenSIPS blocking, and how did we overcome it? Well, so the only way that we could now fix this problem is if we fix this problem from outside of OpenSIPS. So the only way is to reduce the amount of time that blocking event is happening. So an offer command is sent from OpenSIPS to a server anywhere in the world to tell it to expect media from X. When that operation happens, it has to wait for a reply to come in that contains the SDP of the modified response, and also the ports that get opened up. So how is it possible to break the laws of physics and remove that latency when we've got to ask for that information from a remote server? Or how can we predict what the response would look like, so as the ports are allocated in the reply? So we don't break the laws of physics, of course. That's silly. So the only way that we can do this is kind of to predict the future. But we're using a loaded deck, so we know exactly what's going to happen. So this is a typical engagement, again, similar to what you saw before. I flipped the graph around this time. You've got the latency in the middle, London and New York, and we're going to pretend it's 150 milliseconds because that's what that says. And this is the simplified, this is the core bit of what we're looking at. We're looking at the difference between, the latency between OpenSIPS and the RTP. This is the solution that we came up with. So a few extra things that are involved in here, but mainly from the top. Yeah, so basically, let's just jump into this one. Oh, hang on, no. So what we've got now is this OpenSIPS talks to an RTP controller. Doesn't actually have anything to do with RTP apart from to prepare the replies. The RTP is within 1 millisecond of the OpenSIPS server, so that's how that works. This talks to a database. Oh, sorry. I've rested my... Are we back? Slideshow. Okay. Right, sorry about that. Oh, here we go. Right. So, yeah, that's what we're looking at. We've got the OpenSIPS talking to an RTP controller. That talks to a database bus, all within 1 millisecond. We've got eventual consistency between database servers that could be geographically located. And then that bus is in 1 millisecond of what we've called an RTP actuator, which is the bit that does the work. So basically, with this scenario, I'll tell you a little bit more about how it works, but we're looking at the capabilities of reducing what the engagement would have been 150 milliseconds down to 1 to 2 milliseconds. So we're going to have an improvement of maybe about 100. So we can jump from 30 calls per second to, say, 3,000. So it's just no longer a problem. So the way in which we address this as well, because we've got an eventual consistent database here, so that's going to be a bit of a problem, and lots of people just don't like eventual consistent databases. So there's a particular process that we have to go through to make sure that we don't have any problems, any conflicts, any race hazard problems. So on startup, we populate from the RTP controller, we basically say to the database, I want 1,000 ports. So the database says that, and this is done in some type of locking operation or a consistency operation. We either have a quorum on the database or we achieve a lock and make sure that this is true worldwide. This is slow. It's got to talk to everyone, make sure that it accesses and writes the source of truth. When we're talking slow, we're still talking of hundreds of milliseconds. But that's fine. This happens once, and then also if this reservation gets too low, it can just ask for more again. So this operation is asynchronous to the calls being engaged. Then, when OpenSIPS starts the call, it talks from the OpenSIPS controller, OpenSIPS to the RTP controller and to the database bus. It basically says, can I have one of those ports that you've reserved for me? And then it allocates that port. Once that port's been allocated, the database can do an eventual consistent update to other database servers in any other zones. Those other database servers are then going to continue and propagate that information to the RTP actuator. So what essentially is going to be happening is, soon as the database server knows about this update, the database server, I think I've written it's database/bus, sort of does both, as it passes that information onto the RTP actuator, which can then open the ports. In the real world scenario, what we're looking at is essentially somebody picking up the phone when their media is going to be engaged asynchronously to the time that OpenSIPS is engaging it. So it's not really going to be a problem if this eventual consistency is, a few hundred milliseconds. That's not a problem. So now we've got this scenario where each single OpenSIPS instance that we've got can have its own controller, or at least a controller that's located very close to it. Each media zone has its own actuator. We can now use a single controller for each OpenSIPS box, and we can tag each RTP engagement with different properties that then can be listened to by specific zones. So we've now got the capability of having a single media server in OpenSIPS, which basically in the database for OpenSIPS, which means the load up times go much, much faster. It's got super fast response times on that, and we can deploy multiple servers around the world that can be controlled just by a little logic switch in the code when we engage it. And another really cool thing, Anycast. So it was at the 2019 OpenSIPS conference that I first learned about Anycast, and I had no idea how it worked. I chatted with a couple of people, there was a presentation on it, and as I got into a little bit more detail, we said, well, could it be used for this, could it be used for that? Could it be used for media? No, it's useless for media. Why? It's wrong type of thing, we don't really need it. But check out this. Now, what we can do is we can issue a command that goes through, propagates through to the database and everything else. Every single one of these servers can pick up that. So every single server can open up its ports and say, yep, I'm ready to accept this traffic. Obviously, if we do this for, let's say, 6 global servers, only one of the servers is going to pick up the traffic, but the other ones are there ready. So you can process on a little bit further. What's that going to be really useful for? Well, if one of these servers goes down, we can remove that route. BGP will automatically fail over to the next server. So we're going to have, you know, additional levels of resiliency there. And yeah, with Anycast Media, this is the simple scenario. Now, both of these servers are going to be these ones here. Are going to be having the same IP address. So both of these servers both of these endpoints look like they're talking to the same IP address, but these can be differently geographically located IP addresses, servers. And then this is the next level of stuff. This is something else that we can do, which we haven't done yet, but I don't see why we can't do it, is instead of doing it that way, what we can have is we can start to pull off this traffic from the public internet. So if we've got a scenario where we've got somebody in London and somebody in New York and they want to communicate, we can have the traffic being pulled off locally to where they are, sent to a private circuit on some controllable medium where we can have repeatability in terms of the latency that we're having, in terms of packet ordering to reduce jitter. So that seems pretty cool, and I'm really excited to be implementing that. We can still do other types of things as well. This is overall going to give us basically more stability, more flexibility. We can add more servers into the cluster, and the way in which BGP works is going to be fantastic. There's also another protocol which somebody's probably going to tell me about, which will happen within the data center. So if multiple traffic is coming in from on these IP addresses, we can distribute that out. And the big advantage here is that because all of these servers are going to be synchronized together, it means that it doesn't really matter if one UDP packet goes off towards this direction, another one goes towards this direction, because it'll all be handled within the same data center just by distributing that media. So we've got very scalable systems here. So as soon as we start noticing an increase on some servers in the data center, we just spin another one up, tell it to advertise the same IP address. We've got very comfortable scalability. This is where we are at the moment. So we've done a proof of concept, we've done our alpha testing, Anycast testing. Anycast stuff is in progress at the moment. We've pretty much got it working. I actually added functionality onto this because I've realized that there's so many more scenarios that we're going to deal with. At the moment, we've accounted for the very basics of a call coming in and a call going out. We've also got kernel module. We're probably just going to use RTP Engines 1 because that seems pretty robust. It's quite good. But again, we can look into that. And then, yeah, the private circuit. This is going to. Oh no, not again. This is going to be a little bit more long term because I've got to buy them and they're expensive. So thanks very much for listening. Let me know if you've got any questions.
Thank you very much, Jonathan. Any questions? No. You?
So generally, great presentation. Really was interesting about getting a little bit more information about the RTP engine implementation by itself. How do you use the kernel module for part of it, and is the kernel module of RTP support the database integration? And in which actually database are you using? Like some kind of Redis Sentinel behind it or something like that?
Yeah, so great questions. I had a feeling someone was going to ask me about the database. So the database one first. At the moment, we've done our proof of concept with Redis because, yeah, it's got the message bus straight in, and it's and we can we can listen for the updates, and we've got that eventual consistency model. I'm looking into CouchDB, RethinkDB, some things that are proper eventual consistency databases, but that's still a little bit more research to figure out if I'm going to do that. With regards to how this is done, this is just for clarity in case there's any confusion. We're not using anything to do with RTP Engine on this at the moment, apart from making it somewhat protocol compatible in terms of OpenSIPS's engagement. We're probably going to use the kernel module from RTP Engine, which communicates via, I think it's via sockets, system bus, system sockets. That's how we're going to look to implement this later. Yeah, I hope that answers it.
Thank you.
Hey, Jonathan, nice presentation, thank you. I got a question. System seems a little bit complicated. I think when addressing the same problem, we control RTP proxy from B2BA, so it does not have the same scalability issue because it's fully asynchronous. But to deal with this latency problem, we kind of did a little bit different approach. We basically just pre-allocate ports. So as we use RTP proxy ports, we can just have several, allocate them in advance. So it seems like a little bit.
Sounds like a similar way.
Yeah.
So is it the proxy that you use to allocate the ports that remain close to the OpenSIPS? Does the proxy, do you have a...
Yeah, basically we have like, we call it Rtp Cluster, and it's basically middleware that is sitting between like multiple RTP proxies and
So what you're saying is I've reinvented the wheel?
Yeah, but what you did it kind of differently through the databases and stuff.
Yeah,
well, we just pre-allocate those.
So I think we've tackled the same problem in similar-ish ways. Some things the same, some things different. I'll take a little look at that and see if there's anything more I can learn.
So